Welcome to Ask and Learn.
So this problem basically considers the different ways that you can expand a gas and kind of just compares all of them. And so let's see. You have in a cylinder, you have the gas. It's initially at this temperature and pressure and expands till the volume triples. Compute the work done if it's isothermal, adiabatic, isobaric. So this is kind of a straightforward, just like use the formulas that they give. So the first one is what was it again? Isothermal. So for that one, you want to just like literally use the formula. The work done by the gas is NRT, the log of V final over V initial, and then V final is equal to 3V initial, just like that little part's equal to that. So, and then, oh, I forgot my R. Let's get my R in there. What's it? 8.31. I'm just going to double check that. Yes, 8.32. Oh, let me put that in my box. Okay. So joules per mole Kelvin, I believe. Yes, that's right. And yeah, so then it's just to simplify that a little bit, just in case it wasn't clear. NRT, and that's going to be just the ln of 3, because V final is 3 times V initial. And if you plug that into a calculator, maybe you'll get what I got, which is 3289. Doesn't like circles maybe, or if I go too fast. Okay. Great. And so the next one, what was it? It was adiabatic. Adiabatic, Q equals 0. Are these all part A, or is it all? Yes, no, it's not. Okay, great. And I'll go ahead and label that adiabatic. And then we can use our formula, work equals NCV T final minus T initial. Oh no, we don't know the final temperature. So to get the final temperature, we gotta get that. I'm just gonna maybe do it in green so the calculation is kind of clearly a side calculation. So you want to use the equation in the book, T initial, V initial to the gamma minus 1 equals T final, V final to the gamma minus 1 for adiabatic transformations. And then if you do some algebra, which I will go ahead and do for you, involving dividing the VI minus VF, or VI minus VF, and then the TI stays on the outside. And remembering our good old exponent rules, you got T initial times V initial over V final to the gamma minus 1. And yeah, so V final is 3V initial. So then that thing should be like 1/3. And I'm just thinking through, make sure it all kind of makes sense. Yeah, and then this is maybe another point to be clear about. This is the work done by the gas. And I guess I just chose to use this. Maybe that's how it was written when I saw it. Oh, excuse me. This is the work done on the gas. The other one was work by. Okay. So if you calculate that, so you solve for your TF using all this information, using your CV, your 1.2 for the number of moles, you'll get minus 2339 joules. And then work done by is equal to minus work done on. So you can already tell that if for an isothermal process, the work done by the gas is a bit more than if it were done by adiabatically. And I'm not sure if I'm supposed to pontificate about that or not. So I think I'll just keep moving to the isobaric, easy one. The work done by the gas is P delta V. And then let's see. And then your V final, so it's going to be, since V final is 3 times V initial, it's going to be P times 3 V initial minus V initial. And that's just 2P V initial after some algebra. And we don't have V initial, but we can for sure solve for it using PV as nRT. So I'll kind of go ahead and put that in our little kind of preparation box. So then you get that. So I'm going to do the equation here. V is nRT over P. Probably have seen this many times. So it's 2P nRT initial divided by P. So those P's cancel, and I'll go ahead and use red to indicate that they cancel. And then, so it should be just 2 nRT TI. I'm just going to double check because I don't remember actually putting that into a calculator. But maybe I did. So give me 1 second. So I'm just going to recalculate it and see what I get. So it's 2 nRTI. So 2 times 1.2 times R times 300 nRT. So then I got 5987 joules. Again, with the curves, I'm going to redo that. 5987 joules. Is that what I got last time? I don't know. I got something slightly different. But I suppose I trust this more. Great. And so now what we want to do is make the PV diagram. That's, show each process in a PV. So here's V, here's P. Let's start with the lowest hanging fruit. So here's our V initial, not labeling the graphs. That's not the lowest hanging fruit. Oops, and that's not even a point. So I will cut that. So PV initial and then V final, constant pressure. That's what I was thinking is the easiest one. So so there's a constant pressure and then it ends at this one. And and so that's how that looks. And then the other two are just kind of like they're kind of like curves, and like I don't really have like a grid, so I'm just gonna draw them as two separate ones. So like which one is which? Well, let's think about this because the area under the curve is the representation of the work, right? So the one with the bigger area under the curve has it should be the one that more work was done. So in that case, it was, as I said before, it's actually the isothermal one. And so the isothermal one is the one that should have the bigger area. So this is iso, oh my God. It's isoth, okay? And then this one's going to be your adiabatic. Okay, good Lord. And this one's going to be your isobaric obs. Great. So there is this. All right. And what's next? Is it Q? Okay, yep, Q. So, oh, I kind of made my border too big. I'm just gonna like cut it down a little bit. I guess going to new page doesn't really matter. Okay, here's E. So Q equals U, delta U, plus the work done by the gas. So for isothermal, then delta U is 0 because it's isothermal and U depends on changes in internal energy. And then so Q equals the work done by the gas, which we found in like the last part. And then adiabatic. Oops. Adiabatic. What was I writing? For adiabatic, Q should be 0, but I guess I didn't write that in my notes. But that's kind of the definition of adiabatic. Maybe, oh, I was solving for internal energy. Gotcha. Okay, now I know what I was doing. I think the next part also just asks you to consider delta U. So maybe I'll just do that in one part. Yeah, delta U change in internal energy. Okay, so I'm kind of doing this all in one shot. So if Q is 0, then and then yeah, delta U is the work done. It's the negative of the work done by the gas. Oh wait, that can't be right. So of the work done by the gas. Actually, does this make sense? Oh yeah, okay. Delta U is here, delta U minus the work done by the gas. So it's kind of lost energy. Yeah, okay. So it's gone to a lower isotherm, another way to think about it. And then isobaric. Then your let's see, your Q is equal to delta U plus the work done by the gas. All right, and this one, I actually didn't end up doing it ahead of time, so I'm gonna work it out here. So that's gonna be, both of these I think we just have to calculate. Unfortunately, that's okay. NCV T final minus T initial, and but we already calculated the work done by the gas, so I guess we should just calculate this thing, and then what are we missing from that? So we have N, we have CV. Ooh, we do not have T final, but we have T initial. So let's find T final. I'm just going to do a little side calculation here. So from PV equals nRT, T is PV over nR. So T final, V final, P final, V final, which is equal to P initial. The P initial is, P final is P initial, V final is 3 V final, divided by nR. And great. So looks like the ends are going to cancel. I might just go ahead and calculate this instead of trying to do some algebra. So give me 1 second and I will calculate that. So P final, let's see, what was it again? So PV over nR. So 3.6 times 10 to the 5 times V final, which is 3 times V initial. And then V initial is N times R times 300 divided by 3.6 times 10 to the 5. So that's just going to cancel that. So actually, this is getting sort of messy. Maybe I will just write it out just so it's kind of clear what I'm putting into the calculator. So, yeah, actually that actually might be better because, so I can use, that's going to be equal to 3 P initial, V initial, because like I said, P initial is P final. Yeah, divided by NR. And we know that this thingy, PV over NR, is T initial. Ooh, so clever. Which is 300 Kelvin. So the T final is like 3 times 300 Kelvin. So this is 900 Kelvin. So that's kind of a lot. So it's NCV times 900 Kelvin minus 300 Kelvin plus the work done by the gas, which we calculated in the last part. And so now I'm just going to plug into a calculator NCV times 600 Kelvin. So N times CV is 12.47 times 600. So that's 8978 joules. Okay, 8978 joules plus the work done by the gas, which we found in the previous part, which was 5987. Okay, yeah, and this was all Q. So if you add those together, what do you get? 14,965. Okay, so that's a lot of heat that needed to be added. And then our delta U is this. So there's our Q, and then here's our delta U. Boom. Got them all. And let me just double check. There's nothing else. Okie dokie.